Oh, hi everyone, and welcome to the afternoon session. And first speaker is going to be Peter Scholl in his final lecture in this school on pseudo-random correlation functions from Paillier. And Peter, the stage is yours.
Thanks, Benny. This is the last part of this series of talks on PCGs. And the topic here is going to be a little bit different. So there is nothing to do with LPN here, which may be refreshing if you're sick of that. Instead, we'll look at constructing PCGs and more generally PCFs from number-theoretic assumptions like Paillier and factoring-based assumptions. This is a recent work based on a paper from Eurocrypt last year with Claudio Orlandi and Sofia Yakubov. Okay, so I'm going to start by recapping what a PCF is, a pseudorandom correlation function, the definition there. And then I'll present our results similar to the last talk in terms of some kind of general blueprint for how you can construct this kind of object, this time based on the right kind of encryption scheme with some special properties. And then I'll show how we can instantiate this based on different kind of schemes to give PCFs for different correlations like vector VOLE and OT. And then finally, I'll talk about a non-interactive setup protocol for these PCFs, which is based on similar kinds of techniques and allows us to get this special public key setup property to give like almost the minimal level of interactions possible in a protocol like this. Okay, so you've seen this slide a million times before, so I'll skip this, but that's just the motivation. So what we're interested in constructing is a pseudorandom correlation function, which will allow us to generate all of this preprocessing material for MPC. More formally, so we have this key generation algorithm, just like the case of PCG, which outputs a pair of correlated keys to the two parties. And now, instead of having a single expansion step, we want to be able to evaluate this PCF in a kind of random access-like manner, somewhat analogously to a PRF compared with a PRG. So the evaluation function takes as input a public nonce, which is known to both parties, as well as the private key, and then outputs this piece of correlated randomness. So R0, R1 is supposed to be indistinguishable from a fresh sample of the desired correlation. And then for the security property, we again have this notion of security against insiders, where even if one party knows one of the keys, then the output of the correlation should be, in some sense, pseudo-random still, or indistinguishable from a fresh sample. Okay, so what's known about how we can actually build PCFs? Well, there's a few different constructions previously. So that's the most general one is if we use LWE and building on top of special flavors of FAG, which I'll talk about shortly, we can build PCFs for any additively secret shared correlation. So this is just a correlation where you apply some arbitrary function on random inputs and then secret share the results each time you want to evaluate. This is a not very efficient construction. It requires LWE and homomorphic evaluation of a very complex function and even some bootstrapping steps for multiple parties. But you can do it with just a CRS setup and a public key from each of the parties to generate the keys. So it's a nice feasibility result. But if we want something more concretely efficient, there's this variable density variant of LPN, which Yuval talked about yesterday, which we can use to get very simple low degree correlations, including OT, VOLE, even constant degree polynomials. But here we have to pay a bit more in the setup. We have this more expensive trusted setup phase, which generates DPF keys, which you can also replace with an interactive protocol, but it will be several rounds. And then in this talk, the ones I'm going to focus on are instead based on public key type assumptions like quadratic residuosity and the decisional composite residuosity assumption used in Paillier. These constructions can produce correlations for OT or VOLE. And just like the LWE case here, we require only a CRS and some public keys broadcast by the parties. So it's this kind of minimal setup. Okay, so as a warm-up, I want to go through this FAG construction based on LWE at a very high level. So we can build a general PCF from this type of object and then look at how to optimize that construction to get something more efficient. So suppose we have an FHE scheme. In the key generation algorithm for the PCF, we just sample a public key and give out some encryptions of a random seed S, which is going to be used for a PRF. And then in the evaluation phase, the parties have this public nonce as input, which they use to define a program which is going to be evaluated on the FHE ciphertext. So they each locally perform this evaluation, obtain some encryption of an output, and then we rely on a special property of the FHE scheme, which is that the parties can actually take the ciphertext together with some private key material from the setup, and then non-interactively obtain a share of the result. So they get these shares Y0, Y1, where for correctness, we require that they sum to the right thing. So for instance, if we want to produce a PCF for beaver trebles, they produce a beaver treble. And in that case, the program P, which is evaluated homomorphically, will be defined to use the PRF S to generate pseudo-random values A and B, and then multiply A times B. And obviously, evaluating this PRF inside FHE for every time you want to do an evaluation is very expensive and something we want to avoid. But taking this basic blueprint, is there some way of optimizing this? So notice that for the beaver treble case, most of the work is just generating these ciphertexts which encrypt random values A and B. So if we can somehow avoid that, then we just need to do one multiplication and maybe things become a lot cheaper. So for instance, if we had a way of obliviously sampling ciphertexts, so we can somehow agree upon using some public randomness, a random ciphertext to which no one knows the underlying message, then we can do this. Unfortunately, this seems to be a kind of hard problem with LWE, at least. So there are some candidates that have been used in recent constructions of obfuscation based on LWE-like assumptions. But unfortunately, they're super expensive and they require non-standard assumptions. So it's not something we want to go for at the moment. However, this is, of course, a very interesting open problem. And if you can achieve this efficiently, then as well as building I/O from a standard assumption, you would get efficient PCFs. So this is a super nice problem to try and tackle. But in this talk, we'll go for something different and look at different kinds of encryption schemes, which might be easier to do this with. So for instance, the Paillier and Goldwasser-Micali encryption scheme both have a dense ciphertext space, where if you just sample a random element from the ciphertext space, then with overwhelming probability, it should be a valid ciphertext. And the problem, of course, is that these schemes are not fully homomorphic. We only have this additive homomorphic property, which then isn't enough to multiply A and B if we want beaver triples. But we can instead do something a little different, which gets us something close. So this time, our blueprint for building a PCF is going to be the key generation algorithm, where we'll give out some kind of correlated PCF keys, where in particular, one party will get the secret key of the encryption scheme, and another party will get some random value X, which is used as part of a PCF correlation. Then we have the PCF evaluation stage, where instead of doing homomorphic evaluation of encrypted ciphertext, we'll use our nonce and then perhaps feed it through a random oracle to just obliviously sample this pseudo-random ciphertext. So it's an encryption of a random message R, which now only the party with the secret key can decrypt. And obviously we can't multiply ciphertext. So instead, what we're going to rely on is a special kind of shared decryption procedure, which can additionally do one multiplication with this value X, which was distributed to Alice at the start. So you can combine the shared decryption to decrypt shares of R with a single multiplication by some fixed scalar, and then you get these Y0 and Y1, which are shares of R times X. If you see repeating this evaluation procedure many times, each time we get a fresh random ciphertext R multiplied by the same X. So this is exactly a very long instance of vector OLE. So we're going to instantiate this using Paillier encryption to start with. So I'll start with a bit of a background on that. So Paillier works with an RSA modulus n, product of two primes. And then instead of working in the integers modulo n, we'll actually work in the larger group, mod n squared, seen as a group under multiplication. And this group has a special element 1 plus n, which we'll call G, which is special because it generates a subgroup of order n, where the discrete logarithm problem is easy. So to see this, note that if we take 1 plus n and raise it to the power of any x, then if you apply binomial expansion, it's quite easy to see that this just gives you this linear relation, or linear function 1 plus n times x mod n squared. So that means that we can take the discrete log of any element y to the base of 1 plus n by just subtracting 1 and dividing by n over the integers. So this allows us to solve discrete log with respect to this special base, which gives us the special properties useful for Paillier encryption. Another useful fact is that this whole group is actually isomorphic to a product of the integers Zn under addition and Zn under multiplication. And this isomorphism actually exactly defines the encryption algorithm, which takes the plaintext x and some randomness r and encodes this by taking the special base g to the power x times the randomness raised to the power n. And to decrypt the ciphertext, okay, so first, yes, so this encryption algorithm implies oblivious sampling exactly because we have this isomorphism. So any ciphertext that is a part of this ciphertext space can be decomposed into this form and viewed as an encryption of a valid message under some randomness. And finally, in Paillier, the decryption algorithm can be written in this form, where the secret key is just a special integer defined by the factorization of n, such that if we take a ciphertext, raise it to the power d, then we get g to the x. And now we can just solve discrete log to recover x. Okay, so that's everything we need to know about Paillier. And with this, let's take a closer look into this shared decryption algorithm. So we'll start with a simpler case where we just want shared decryption without multiplication. So the parties both have this ciphertext encrypting a random value r, and then they have additively shared this special secret key d, or in this case, subtractively shared over the integers. And the goal of shared dec is to output shares of the encrypted value r. So parties will start by applying decryption on their shared secret key. So take the ciphertext, raise it to the power d0 or d1. Since c to the d gives us g to the r, then now the ratio of these two group elements, g0, d1, will be g to the power r. There should be an exponentiation there on the slide. So this is kind of some kind of nice relation, but it's not quite the additive relation we want on the final output shares. So the final goal is to run a distributed discrete log procedure where the parties can non-interactively convert this divisive sharing of g to the power r into an additive sharing of the value r, which will be shared modulo n. Okay, and then building on that, if we can do shared decryption, what we additionally want to do, remember, is actually shared multiplication, where we additionally multiply by the scalar x whilst we're decrypting. Oh, sorry, scalar y now. So in this case, as a setup, instead of shares of the secret key, we require shares of the secret key times by y. And now the parties just run exactly the same thing, raise the ciphertext to the power of their share, and this time instead of g to the r, we get g to the r times y when we take the ratio of the two group elements. Now again, if we have a distributed discrete log procedure, we can just convert these group elements into additive shares modulo n of r times y. Okay, so if we can do that, then we can plug this into the PCF blueprint and get a PCF for vector OLE. So the only missing piece is this distributed discrete log algorithm. So this problem of finding a distributed discrete log goes back to the DDH setting, where it was studied for homomorphic secret sharing in 2016. So I'll recap the challenges of the DDH setting before going into how we do this over Paillier to make this work more efficiently. So suppose Alice and Bob have this divisive sharing of group elements G0, G1, which is G to the XY, where here now G is just going to be a generator of the entire group, not this special element in Paillier. Okay, so we'll look at these group elements on a circle where we kind of separate each item by multiplying by powers of G, which represents the entire group generated by G. And now if Alice and Bob can somehow measure the distance in terms of powers of G between their two group elements, and then they can get X and Y. So we want to do this in shared form. And one candidate approach for doing this is agreeing on some fixed element in the group, say some element H, and then measuring the distance from G0 and G1 respectively to H. So if we do this by just counting the number of multiplications by G in each case, we get an integer, which should then be an additive, or in this case, I think subtractive share over the integers of the correct value X times Y. Okay, but there's a couple of problems here. So firstly, if either of these shares are large, then you're just counting this number of multiplications until we get to H is going to be prohibitively expensive. So it's going to be exponential time in the worst case. So one workaround for this is to have several distinguished elements. So we can have some pseudo-random way of determining whether a particular group element is distinguished or not, and then choose the density of these appropriately so that we have enough of them. Another problem we have, of course, is that this restricts us to a polynomial-sized message space. Because it's kind of inherent that these two share sizes, xy0 and xy1, will have to be at least the size of the message. And again, if we have very large messages, we're going to get into this extremely inefficient range we want to avoid. So that's a kind of inherent limitation. But then finally, there's another really annoying problem, which is that once we have many of these distinguished elements H, of course, they might not end up finding the same H. So if there's another element in between Alice and Bob's initial group elements, then we'll get inconsistent shares when they try to measure this distance. So with probability inverse polynomial in the security parameter, we end up having this probability that they get the wrong thing. So even with this inverse polynomial error probability, this algorithm is useful for certain things. It gets you this homomorphic secret sharing scheme, which has many interesting applications for MPC. So there's been a lot of effort to improve this and give various optimizations for reducing the error. But despite all this, it's still computationally quite heavy. And there's always this inverse polynomial probability of correctness error and the limitation to small message spaces. So there was also another variant used in Paillier groups, which actually had the same limitations as above and didn't manage to overcome them. So of course, the question is, can we somehow do better by exploiting the special structure of the Paillier groups? And interestingly, there was this work from Crypto 2018, which studied this discrete log or distributed discrete log problem in a more general framework and showed that solving this reduces to solving some variant of the discrete logarithm problem. So it's unlikely to be able to improve upon this correctness error from previous works. However, if you look at this reduction and apply it to the Paillier setting, then it simply translates to solving discrete log in the subgroup where Paillier is easy. So if we now plug this into the Paillier setting and work in this special subgroup, so where we replace this element G with the special element 1 plus n. Now 1 plus n doesn't generate the whole group. So instead, when we look at this circle, we're actually looking at a coset of elements in the group defined by, say, G1, Alice's element, and then multiplying by powers of 1 plus n. Okay, but we can try to do the same type of approach. So if we use just a single distinguished element here, which is what we want to aim for if we try to reduce the correctness error in the previous approach, then the parties can measure their distance to this element by just taking their input group element, dividing H by their input, and then this gets us some power of 1 plus n, to their share, and then they can apply the discrete log algorithm with this base to recover the share. This is essentially all works just because the discrete log algorithm is easy in this group. However, the only challenge is that they have to agree upon this element H, right? Because we're not in the whole group anymore. We can't just pick a random group element. We have to find one that lies in the same coset defined by the element G1. It turns out if they both just define H by taking G1 modulo n or G0 modulo n, firstly, this gives the same value, which is quite easy to see from the fact that G0 over G1 is 1 plus n to the xy. And secondly, this gives us something which lands in the right coset. And as long as that's true, then we can always apply this discrete log algorithm, and we get something which ends up working with an exponentially large message space and a negligible probability of error for this share conversion procedure. Okay, so I'll just go through this in a little bit more detail and show why this works. So we have these two inputs, group elements G0 and G1, where after the first part of this shared decryption protocol, we know that G1 is equal to G0 times 1 plus n to some power z. And the goal is to agree on this element H, which is in the same coset as G0 or G1. Where I said if we define H to be just G0 mod n, which equals G1 mod n, then this will be the case. Okay, so why is this true? I'll just switch to my pen here to go through this proof. So we want to find such an H. So let's first suppose that we have an H. So suppose H is equal to G0 times 1 plus n to the power I for some I. Okay. So then we can rewrite this slightly by taking G0, representing it as H plus some H prime times n. So remember, H is G0 mod n. And then on this right-hand side, we have this nice fact from Paillier that we can write this as 1 plus I times n mod n squared. Okay, so now multiplying this out, we get H equals H plus H prime plus I times H n, and then reduce mod n squared, the rest goes away. And now remember, we want to solve this to find I. So first we can see that these H's cancel out, and then we get I Hn is minus H prime n. This is mod n squared, so if we divide by n, then we end up with a relation modulo n. So we actually get I is equal to minus H prime H inverse mod n. So if we can compute this, so as long as H has an inverse mod n, which it always should do if we start with this, then we can compute this I such that H lies in this coset. And we are done with distributed discrete log. Okay, so so go back to the PCF for vector OLE a second. So we've seen how it works, and before moving on, I want to give a slightly different perspective on this. By viewing this in the same way that Yuval presented this PCF from variable density LPN yesterday, in the lens of a weak pseudorandom function. So we have this procedure where we're taking a random ciphertext C, and we're essentially decrypting it to get a random message. And if we look at this as a function depending on the decryption key with input this random ciphertext, then this is actually a weak pseudorandom function, where we call that a weak PRF is one that is secure as long as the input, in this case C, is a random value. So we take a random ciphertext, and assuming pay is secure, this gives us a random message. So now when we're giving out these additive shares of d times y, so we can do this distributed multiplication and decryption to shares. And this is kind of equivalent to giving out FSS keys for a function class, which is scalar multiples given by y times the evaluation of the weak PRF. So this is how you can see this as an instance of this framework, which I think isn't so helpful for coming up with the construction, but is interesting to compare it with the other types of constructions we know. Okay, so another variant we can do with the same kind of construction is getting a PCF for oblivious transfer. And here, well, it's essentially take the same thing, but instead of Paillier, we'll plug in a different encryption scheme, which is going to be Goldwasser-Micali. And recall that for OT, it's enough if we can just build correlated OTs, which is this batch of OTs where the receiver's messages are of the form yi equal to ri, the secret choice bit, multiplied by this fixed delta known to the sender, plus some other random string y1 known to the sender. If we can get correlated OTs, then we can always hash these to get random OTs, and that's enough. Okay, so in the Goldwasser-Micali encryption scheme, unlike Paillier, which encrypts integers mod n, here we're just encrypting a single bit. And this bit is going to translate it into the choice bit in the OT. And ciphertexts now are just elements of the integers mod n instead of n squared. And we can define this secret key very similar to the Paillier case, where if we take a ciphertext C and raise it to the power of the secret key, and we get this special element -1 raised to the power b. So now this is either 0 or -1, depending on the bit. And you can kind of view this as mapping into a subgroup of size 2, where the discrete logarithm problem is easy, analogously to Paillier, which maps it into this subgroup of size n, where the discrete log is easy. Okay, so given this encryption scheme, we want to construct now a distributed discrete log algorithm. But now, because we have a plaintext space which is only a size 2, this is actually really easy. We can basically just do the trivial brute force method. So on input is ciphertext, let's call it y. We just want to map it into 2 distinct cases, which will be consistent with what the other party does. So we're going to say if y is less than n/2, we output 1, otherwise we output 0. So now if we give them 2 y's, which have this ratio of -1 to the b, which we'll get if we try to decrypt with shares of the secret key, then we take the DDLog and XOR these together, we actually end up with the right bit b. That's because if one of the things is less than n/2, then when we flip the sign, we end up in the opposite case. So you can see this as equivalent to XOR. Okay, so given this, the PCF is pretty simple. The only catch compared with the Paillier case is we now have to repeat this bit by bit to be able to build up correlated OTs, which are of the length we require. So if we want them to be like the security parameter, as is common, then we have to do this security parameter times, giving out shares of the secret key times each bit. And then we sample an oblivious ciphertext, which will be the receiver's choice bit, and then run this shared decryption procedure to get some shares of Ri times delta. So the main cost of this is just repeating this lambda times, where we have to do 1 exponentiation modulo n for each of these bits. Okay, so for a quick summary of the PCFs, the ones we've seen from number-theoretic assumptions build these 2 correlations, either VOLE in Zn or correlated OT, or equivalently random OT if you use a hash function. And first off, for the key generation phase, we require this special setup, which for the Paillier case is just additive secret shares of the integers of a secret key times by this fixed scalar x. Whereas in the QR case, we just need to repeat this lambda times each bit delta I. And then the cost per eval is just 1 exponentiation for each of these elements, which to generate OT actually ends up being quite a lot. We have 128 exponentiations. For both of these, the key size is actually really small. And even when you have 128 of these, we still get a key of only around 50 kilobytes for QR or 1 kilobyte for Paillier, which is way, way smaller than even the PCG constructions from LPN. So one natural question is to wonder, okay, can we take this PCF for vector OLE and then use it to somehow build a PCF for OLE, where we can get independent multiplications instead of always multiplying by the same x. And if you look at the setup phase of the Paillier construction, you might think like, okay, this is kind of an OLE. So what if we instead have a bunch of different setups with the same D and different x's? Then this is like a vector OLE. So maybe we can do some kind of bootstrapping and extend this. One problem here is that the setup shares have to be of the integers for decryption to work. Because when we do exponentiation, we work modulo the order of the group. So you can't directly bootstrap using the same PCF because the PCF gives outputs modulo n. However, what we can do is build a separate PCG or PCF from an LPN style assumption where we tweak the PCG slightly so that it outputs something that can be viewed as shares over the integers. And we use this to generate the setup for the Paillier construction, and then kind of bootstrap from there to repeat the Paillier construction a batch of times and get OLEs, or even PCF for arbitrary decree 2 correlations by combining these two things. So here the setup cost is roughly proportional to the setup cost of the PCG for vector OLE, and then the computational cost for evaluation is going to be similar to the PCF for vector OLE from Paillier, where we have 1 exponentiation per output. But now we have the extra key size coming from the LPN-based construction, as well as the extra assumption. So it's kind of a hybrid of both worlds. It inherits both the best and the worst parts of each of them. And finally, we can also compare these with the VDLPN-based construction. So looking back to that one, the main disadvantages of VDLPN are that we have this more costly setup phase. We use many distributed point functions. It's not constant round to generate these keys using a secure protocol. And again, the key sizes are quite large. Depending on the flavor of assumption you use, whether it's a conservative or less so, the key size ranges from 100 kilobytes or so up to a couple of megabytes. And of course, these assumptions are somewhat new and untested, and I'd like to see more research in this area. Of course, the big benefit of using LPN is that we avoid all these expensive exponentiations in RSA groups, and we have much faster computation. So as a rough estimate, with the most aggressive choice of parameters for VDLPN, we can do about 20,000 evaluations a second on 1 core of a modern CPU. Whereas doing Paillier exponentiations, these are super slow, modulo n squared. You can only do about 100 evaluations a second of your vector OLE. And with OT, this gets even worse because you have to repeat this 128 times. So there's maybe a couple of evaluations a second. So these number theoretic ones, they're super simple. They have really small keys. They're very implementable. So if you don't mind these slow evaluation times, it's fine, but it's not so scalable. So VDLPN still seems like a competitive candidate from that respect. Okay, so maybe I'll pause and see if there's any questions from that.
No, absolutely no questions so far.
Okay, great. And how are we doing for time? I guess okay. So I'll just mention as a quick aside that these techniques we've shown for Paillier can also be used to construct homomorphic secret sharing. So homomorphic secret sharing is kind of the jewel of function secret sharing, which Alec talked about on Sunday. We want to be able to secret share inputs and then locally evaluate some program on the inputs to obtain shares of the outputs. By applying this shared decryption technique, we can get HSS for a class of special restricted multiplication circuits where each multiplication gate in the circuit has to be between an input wire and an intermediate value in the computation. It turns out this class of circuits is roughly equivalent to log depth circuits or branching programs. The idea of the construction is very simple, and we just give out encryptions of the inputs to the program, and as well as secret shares of the secret key. And then for each multiplication, we use this shared decryption algorithm to combine and pair together these encryptions with the secret shared intermediate values and do one multiplication. And this constraint on the multiplication gates exactly fits the constraint on the multiplication algorithm we have from Paillier already. So of course, compared with previous HSS constructions like DDH, we have exactly the same advantages of the share conversion algorithm, where we can get this negligible correctness error and exponentially large plaintexts, which weren't possible with previous constructions. And you can also compare this with lattice-based constructions of building HSS, which are a bit more efficient in terms of computation, because if you use ring LWE, the computational costs are much faster than Paillier. But on the other hand, Paillier ciphertexts are smaller than ring LWE ciphertexts, so there's some trade-off there. Okay, so that's enough on HSS. The last thing I want to talk about today is concerning the setup phase of the PCFs. So remember, in both of the cases, we essentially have the setup, which is just additive secret shares of a single product or a set of products, where one party has a secret key D, and then the other party either has a scalar X or bits delta I. Now, both of these things are just instances of OLE, right? So we can have a setup protocol where the parties just run one OLE, generate these shares, and then they're done. Okay, but what's the minimal level of interaction we can do this setup with? So a standard OLE protocol, at least the ones I talked about on Sunday, these are two messages. So we have a message from the receiver and a message from the sender. But in this sharing kind of setting where we're just generating shares of a single product, can we do this with a single parallel message? And this type of setup would give us then this public key flavor of setup where Alice and Bob can independently generate a public key, broadcast this once and for all, then use their private key to derive the PCF keys. And it turns out by exploiting the same kinds of share conversion techniques which we use to build the PCFs, we can also build this public key setup in a single round. Okay, so I'm going to describe this construction quickly. Again, switch to the pen. So let's say Alice and Bob each have X and Y. The goal is to obtain shares of X times Y. Practice, we want it over the integers. Here we're actually going to do it modulo n for some RSA modulus. If you want it over the integers, then you can just choose this n here to be much, much bigger than the bound on the integers you want. So you choose it to be a different RSA modulus than the one you actually use in the PCF, and then you can view the shares over the integers, essentially. But anyway, in the construction, we'll have a CRS, which is going to be this RSA modulus n, which is p times q, where nobody knows the factorization. So this is a foremost trusted setup, but just a one-time setup. And then we additionally have two random group elements, let's say G bar, because we've already used G, and an element C, which are both sampled from Zn squared. Okay, now given this CRS, we want Alice and Bob to each send a single message and obtain shares of X times Y. So the idea basically follows a classic OT protocol from the 90s by Paillier and Bacali, which itself is very similar to Diffie-Hellman key exchange. So let's just start by looking at Diffie-Hellman. So suppose Alice sends G to the R. Let's call this some group element A. And Bob sends G to the S. Let's call that B. And okay, we want to actually incorporate the inputs in the message. So we're going to have Alice multiply her G to the R by C raised to the power X. Now, this isn't the full protocol, but let's just look at what happens here if we follow in the spirit of a Diffie-Hellman key exchange. So Alice can define a key. Let's call it K0, which is Bob's message raised to Alice's secret R. Okay, so this is, of course, G to the RS. And similarly, Bob can define a key, K1, by taking A to the power S. And this is now going to be, okay, G to the RS, but we have this extra term from C to the X. So we get C to the XS. Okay, now if we look at the ratio of these two keys, K0 and K1, what we have is this C to the XS term. Remember, if we want to apply distributed discrete log, then we want Alice and Bob to get two group elements where the ratio is actually going to be, say, some 1 plus n to the xy, so that they can decrypt it locally and get shares of xy. So if we can somehow switch this C to the XS to be 1 plus n to the xy with a bit of correction value, then we can make this work. And we'll do this by having Bob send one more value. Let's call this D. And this is going to be C to the S, so his secret S, now multiplied by 1 plus n to the power y. Okay, and we do the same computation as before. So now Alice ends up with something slightly different. She has B to the R, which is, and she takes this and, yeah, okay, she will now multiply this by D to the power X to incorporate both of the inputs into this key. So this gets us G to the RS, now times by C to the SX, and finally 1 plus n to the x times y. And now if we look at the ratio of these two things, well, the C to the XS cancels out. We have this on both sides. And the only thing that's left is this 1 plus n to the power xy. So if we feed these two shares into the DDLog procedure, then what we end up is additive shares modulo n of x times y. Okay, so that gives us something correct, exploiting DDLog. A quick note about security. So if we look at the messages that Bob sends, so we got this kind of G to the S value, and then C to the S times by 1 plus n to the message. So G and C are these random CRS elements. You can kind of view these as an Elgamal public key, and this is now like an Elgamal-like encryption in the Paillier group. Because G and C are CRS, no one knows the corresponding key, so no one knows the discrete log of C to base G. So this hides Bob's message Y. On the other hand, for security, when Bob is corrupt, if we look at Alice's message, well, we have G to the R. This was a random group element, and we can show that under the Paillier assumption, this hides the X when multiplied by C to the X. So this gives us a passively secure protocol where we have a single round to, with minimal interaction, generate the shares of X times Y. Okay, so just to recap this whole public key PCF, I'm just going to give a quick summary of the protocol flow when you put all of this together. So we have the CRS setup, which gives out this modulus, which the parties then use for their OLE message to set up the keys. So using DDLog, they can obtain the right shares and get their PCF keys, which each party then feeds into the eval algorithm, given some public input I. And then they can use this to generate as many OTs as they want, or vector OLEs as they want, completely silently. And this is the public key PCF kind of protocol flow for any PCF with this nice non-interactive setup property. Okay, so to conclude, we've seen PCFs and a pretty general blueprint for constructing these things, starting from the general expensive construction from multi-key FHE, and then trying to optimize this via oblivious ciphertext sampling, and an encryption scheme that supports this special decryption into shares. We can instantiate this with Paillier and Goldwasser-Micali to obtain very simple, reasonably efficient, I would say, schemes. Not great, but certainly usable in some scenarios, I would say. And we get these PCFs with a very cheap setup, but somewhat expensive computation. We also have this non-silent OLE protocol from Paillier, which is used to generate the setup procedure with this simple one-round protocol to get the public key setup. So there's a bunch of open problems in this kind of area, which I think are interesting. So first off, I think it'd be really nice to take this general blueprint of building PCFs and see what other encryption schemes can be used to be plugged in there. So Paillier and Goldwasser-Micali are just the first ones we found. There might be others which work naturally, or maybe we can design new schemes which have this right ciphertext structure so you can sample obliviously. The advantage of doing this is we might be able to obtain PCFs for different correlations. If we can do this with a, say, a different kind of homomorphic encryption scheme or a functional encryption scheme may be interesting, as well as building PCFs from different assumptions. On a related note, I think it would be really nice to have something to generate OT, avoiding this security parameter blowup when we plug in Goldwasser-Micali. So one potential way to do this would be have something where we don't have to work one bit at a time. So for instance, in Paillier, if we could obliviously sample a ciphertext, which we know encrypts a single bit, then we could actually already do OT immediately, because then we could view that as a vector OLE, where the receiver's inputs are always 0 or 1, and then see this as a correlated OT and hash to get random OT. Unfortunately, this seems like a really hard problem with Paillier, but maybe there are other encryption schemes where you can actually make this work. And thirdly, for the public key part of the PCFs, we, of course, rely on this CRS, which is the trusted RSA modulus. So having something without that setup would be nice to have. And then finally, this is something I also mentioned in the previous talk, is that for the LPN-based PCGs or PCFs, we currently have at least a 2-round setup to generate the punctual PRF keys. It'd be really nice if we can replace this with this nice public key flavor setup with just a single parallel message from each party. And finally, one big tricky question, I think, for a lot of these kind of constructions is going beyond 2 parties. So this chair conversion procedure and distributed discrete log, if you try to apply this with 3 parties, it doesn't seem to work. Also similarly for LPN-based constructions, even if we move to distributed point functions in the 3-party setting, and then these are much, much less efficient than the 2-party ones, which introduce challenges when you want to build certain kinds of PCGs or PCFs in these settings. So that's everything I wanted to cover. So happily take any more questions.
Unfortunately, there are no questions in the Slack, but maybe I can ask one. So sure. If you go back to the big picture from the beginning with the secure computation with preprocessing, can you maybe give an overview from an implementation and framework point of view, which of those protocols that you covered in the past days are available in which kind of frameworks?
Right. So that's actually a slightly less satisfying answer, I think. So because this PCG stuff is all very recent, at least in terms of general MPC frameworks, they haven't yet been implemented to generate the preprocessing. So I guess for dishonest majority activity secure MPC, then the 2 big frameworks are Scale Mamba and MP Speeds. And both of these still use homomorphic encryption or OT directly to build multiplication triples. On the other hand, there are some implementations of at least the silent OT and vector OLE constructions based on LPN. So no, there's a couple of libraries like libote, Peter Rindle's library for OT extension, and then also what's it called, the EMP toolkit for general kinds of 2PC and MPC protocols like garbled circuits and secret sharing. They support the silent OT protocols and even vector OLE. But I think they haven't been plugged into the MPC protocols to exploit their full capability yet.
All right, thank you.
Okay. Thank you, Peter. Thank you for this lecture and for the 4 lectures you gave in the school. We enjoyed them very much, and I'm sure that they'll be very useful. I mean, they were very useful for me, and I'm going to go back to them and read them more, watch them more carefully. So thank you, and we're going to meet again at 3:15 Israel time for the next lecture.
Great. Thanks, Benny.